Hello. This is Andromeda again, test number 23187600230. Welcome to the Deepwater and High Pressure High Temperature course. MSSDRF 1.109. This course is completely powered by Artificial Intelligence Algorithm. Introduction to Challenges in Drilling Operations. In this course, it is very important to shed the light on the term challenging drilling operation, as it will help the student to understand the nature of the material that he or she is going to go through, as challenging in the classroom and in the field. We borrow a citation from SBE paper published on the 4th of October 2009. Currently, some of the most challenging wells being drilled by our industry are located in deepwater zones in the Gulf of Mexico. Many of those wells are in water depths of 8,000 feet or more, and several are targeting reservoirs around 30,000 feet and beyond. The student will understand directly that water depth alone is challenging too. The tools used in location, drilling hands, and logistics and contingency plans. In addition to a targeted depth, which is another challenge to encounter. Another citation that deserves the mention is an SBE 1 Petro published on the 24th of October 2017. Petrobras has also set a new Brazilian record for exploratory drilling by reaching a water depth of nearly 3,000 meters. Petrobras broke the record for the deepest exploratory oil well in Brazil, with a depth of 7,700 meters. The drilling was in the pre-salt region of the Espírito Santo Basin, 145 km off the coast, in an area known as Manai. The news was released by the company this Friday, the 10th of October 2021. The number of wells being designed or proposed for drilling in difficult and challenging locations increases day by day. The normal and everyday skills of oilfield professionals should be upgraded to qualify them to face those challenges with the correct knowledge and transferred experience to avoid a disastrous unprofessional attitude that represents a serious and life-threatening state or condition that should be mitigated. The oilfield service hands like drilling fluids engineers, cementers, casing installation, and drilling engineers, geologists, mud loggers, even drilling crew, should have a certain degree of knowledge and adequate transferred experience and technical awareness before assigning them to a challenging drilling project, like Deepwater or HPHT well. For the first time, cementing and well control are among the top technical priorities that require adequate awareness in hot and highly pressurized zones. Understanding the basics of drilling and drilling fluids is mandatory before attending this course, even though some might take it at their own pace of understanding. Executing a challenging drilling operation project. One of the important questions that haven't a definite answer is when to move forward with a challenging drilling project. For example, a deepwater drilling project. The answer can be summarized in Square 1 is economics, reservoirs with high flow rates and commercially thick drainable reserves. Then comes technology. Accurate seismic and geological data confirm that this well is drillable with the current technology in our hands. The difference between conventional drilling operations and challenging drilling operations is the cost and difficulty. It is a common concept to seek cost reduction in those wells due to the substantially big investments needed to drill such projects. If funds are available and technology, crew, and safety are manageable, then comes the execution of the project. In challenging drilling operations like deepwater drilling, the increase in water depth is the bar that increases gradually, from the 60s until the deepwater technology reached a depth close to 11,500 feet, which is equal to 3,505.2 meters. It would be an act of negligence if we didn't consider the environmental impact of deepwater drilling, as the world of deepwater drilling has evolved, more cautious and skeptical since the blowout of the Macondo well that occurred in the Gulf of Mexico on the 20th of April 2010. The Macondo incident, Gulf of Mexico on 20th of April 2010. On April 20, 2010, the oil drilling rig Deepwater Horizon, operating in the Macondo prospect in the Gulf of Mexico, exploded and sank, resulting in the death of 11 workers on the Deepwater Horizon, and the largest spill of oil in the history of marine oil drilling operations. 4 million barrels of oil flowed from the damaged Macondo well over an 87-day period, before it was finally capped on July 15, 2010. On December 15, 2010, the United States filed a complaint in district court against BP Exploration and Production and several other defendants alleged to be responsible for the spill. The final findings by the committee are summarized in the following 7 points that are very interesting. 1. The flow of hydrocarbons that led to the blowout of the Macondo well began when drilling mud was displaced by seawater during the temporary abandonment process. Finding 2.1. 2. The decision to proceed to displacement of the drilling mud by seawater was made despite a failure to demonstrate the integrity of the cement job, even after multiple negative pressure tests. This was but one of a series of questionable decisions in the days preceding the blowout that had the effect of reducing the margins of safety, and that evidenced a lack of safety-driven decision-making. Finding 2.2.
Hi, this is GIF, Andromeda's assistant. She went for a break to check her neurons. Let us continue with the committee finding. 3. The reservoir formation, encompassing multiple zones of varying pore pressures and fracture gradients, posed significant challenges to isolation using casing and cement. The approach chosen for well completion failed to provide adequate margins of safety and led to multiple potential failure mechanisms. Finding 2.3. 4. The loss of well control was not noted until more than 50 minutes after hydrocarbon flow from the formation started, and attempts to regain control by using the BOP were unsuccessful. The blind shear ram failed to sever the drill pipe and seal the well properly, and the emergency disconnect system failed to separate the lower marine riser in the Deepwater Horizon from the well. Finding 3.1. Finding number 5 is very alarming and should raise awareness among professionals. 5. The blowout preventer system was neither designed nor tested for the dynamic conditions that most likely existed at the time that attempts were made to recapture well control. Furthermore, the design, test, operation, and maintenance of the blowout preventer system were not consistent with a high reliability, fail-safe device. Finding 3.16. 6. Once well control was lost, the large quantities of gaseous hydrocarbons released onto the Deepwater Horizon, exacerbated by low wind velocity and questionable venting selection, made ignition all but inevitable. Finding 4.1. 7. The actions, policies, and procedures of the corporations involved did not provide an effective system safety approach, commensurate with the risks of the Macondo well, the lack of a strong safety culture, resulting from a deficient overall systems approach to safety is evident in the multiple flawed decisions that led to the blowout. Industrial management involved with the Macondo well Deepwater Horizon disaster failed to appreciate or plan for the safety challenges presented by the Macondo well. Finding 5.1. Conclusion. This incident causes and reasons will be a motive and inspiration for many active and inactive professionals in the oil and gas industry to reveal exactly what happened on that day, and this will take a long time to settle. This is a very well-made video on YouTube analyzing the incident selected by Andromeda. The CSB is an independent federal agency charged with investigating industrial chemical accidents. Headquartered in Washington, D.C., the agency's board members are appointed by the President and confirmed by the Senate.
April 20th, 2010. 11 workers died and 17 were seriously injured by an explosion on the Deepwater Horizon, an offshore drilling rig located approximately 50 miles off the coast of Louisiana. The rig burned for 2 days, eventually sinking and triggering the largest oil spill in U.S. history as oil and gas spewed up from the sea floor. The Deepwater Horizon had been drilling an oil well in 5,000 feet of water in an area of the Gulf of Mexico known as the Macondo Prospect. In 2010, the CSB launched an investigation to examine the technical, organizational, and regulatory factors that contributed to the accident. During the investigation, the CSB made new findings about why a key piece of safety equipment, the Deepwater Horizon's blowout preventer, failed to seal the well during the emergency. These new findings help explain why the accident was so devastating, and the CSB cautioned that other blowout preventers currently in use could fail in similar ways. Drilling an offshore well involves creating a pathway between the drilling rig and oil and gas reservoirs trapped beneath the sea floor. A deep hole, or well bore, is drilled through layers of subsea rock and sediment. These rocky layers can contain trapped water, crude oil, and natural gas under pressure. An unplanned flow of these well fluids into the wellbore, known in the industry as a kick, can be dangerous. Without careful management, a kick can lead to a blowout, the uncontrolled release of flammable oil and gas from the well. A blowout can be catastrophic, since oil and gas reaching the drilling rig can quickly find an ignition source, leading to a fire or explosion, endangering the lives of the drilling crew. To prevent kicks, drillers pump a dense slurry called drilling mud into the well, creating a barrier between the undersea oil and gas and the piping that leads to the rig. If this mud barrier fails or is somehow removed, the safety of the drilling crew depends on a critical piece of equipment located on the sea floor called the blowout preventer, or BOP. The BOP is a complex electrically and hydraulically powered device that is essential for controlling the well and, in an emergency situation, preventing a disaster on the platform high above on the sea surface. The BOP is connected to the rig by a large diameter pipe called a riser. If a kick occurs, the blowout preventer is designed to prevent flammable oil and gas from traveling up the riser to the drilling rig. This is done by sealing the area around the drill pipe, known as the annular space. To do this, the crew can manually close pipe rams and donut-shaped rubber devices known as annular preventers. If those devices should fail to work, the last resort is a pair of sharp metal blades which form a blind shear ram designed to cut the drill pipe and seal the well. The blind shear ram can be activated manually or by automated emergency systems. At approximately 8:45 p.m. on April 20th, 2010, a kick occurred in the Macondo well. Oil and gas entered the well bore undetected, eventually passing above the blowout preventer and traveling quickly up the riser toward the Deepwater Horizon and the 126 people on board. Just after 9:40 p.m., drilling mud, forced upwards by the rising oil and gas, suddenly blew out onto the rig. Crew members responded by closing the upper annular preventer in the BOP. However, this did not seal the well as intended, and flammable oil and gas continued to flow into the riser toward the rig. Next, the crew closed a pipe ram. This successfully closed the annular space and sealed the well, but tragically this proved to be only a temporary fix. Oil and gas that were already above the pipe ram continued to flow inexorably toward the Deepwater Horizon. As the oil and gas escaped the riser onto the rig, the pressure dropped in the annular space above the pipe ram. But at the same time, the pressure in the drill pipe climbed substantially. The drill pipe was closed at the top, but oil and gas continued to flow in from the reservoir below. After extensive analysis, the CSB concluded that this large difference in pressure likely caused the drill pipe to buckle, essentially bending the pipe off-center inside the blowout preventer. The buckling pushed sections of the drill pipe outside of the reach of the blind shear ram blades. This would eventually prove to be catastrophic. At approximately 9:49 p.m., the flammable hydrocarbons found an ignition source, and the first explosions shook the Deepwater horizon. With the drill pipe buckled, the explosion and subsequent loss of electrical and hydraulic power from the rig likely activated an automated system on the blowout preventer known as the AMF deadman, which closes the blind shear ram and cuts the drill pipe. This emergency system is designed to activate when electric power, hydraulic pressure, and communications from the rig have been lost. The AMF deadman system was operated by two redundant control systems on the BOP, known as the yellow pod and the blue pod. The redundancy is supposed to increase the reliability of the system in an emergency situation. The yellow and blue pods worked independently of each other and were comprised of identical enclosed computer systems and sets of solenoid valves. When activated, the solenoid valves controlled important BOP functions, such as closing the blind shear ram. If electrical power from the rig was lost, as happened on April 20, 2010, both the yellow and blue control pods contained backup 27-volt and 9-volt batteries to power emergency functions. The 9-volt batteries powered computers that would activate the solenoid valves, which were powered by the 27-volt batteries. However, evidence indicates the blue pod had been miswired at some time before the BOP was lowered onto the seafloor. This caused the pod's 27-volt battery to drain and made it impossible to operate the solenoid valve for the blind shear ram on the night of the accident. And within the redundant yellow pod, the solenoid for the blind shear ram had been miswired. The solenoid valves were controlled by two coils of electrical wire. These two coils were designed to work in concert, generating a magnetic field strong enough to operate the valve. But within the miswired solenoid valve, the two coils actually opposed each other, leaving the valve paralyzed. Only a third unplanned failure allowed the yellow pod to operate. On the night of the accident, one of the 9-volt batteries that powered the solenoid valve's computer had failed. As a result, the affected computer system could not initiate the command to energize the miswired coil. Had both coils of the miswired solenoid valve been energized, the two coils would have generated opposing forces on the valve. The solenoid valve would have remained closed, and the blind shear ram would never have been closed. However, the failed battery rendered one coil inoperable, and most likely allowed the other coil to open the solenoid valve by itself. This in turn initiated closure of the blind shear ram. This should have cut the drill pipe and sealed the well, greatly reducing the impact of the accident. But because the drill pipe was buckled and off-center inside the blowout preventer, it was trapped and only partially cut. With the failure of this last-ditch measure, there was nothing left to stop the massive oil spill and the destruction of the rig. During its investigation, the CSB identified a mechanism that likely caused the drill pipe to be buckled around the time of the explosion. This mechanism is called effective compression. Although effective compression had previously been noted as a hazard in other drilling operations, it had never been identified as a problem affecting drill pipe during well operations. Effective compression occurs because although pipe may appear to be perfectly straight, in fact it has minute bends and irregularities, invisible to the naked eye. Along these bends, the side of the pipe that is curved outward is slightly longer and has more surface area than the other side. When there is a large difference in pressure between the inside and outside of the pipe, as happened on April 20, 2010, the longer side of the pipe experiences a larger bending force. Eventually, this force can become great enough to buckle even heavy pipe. This is an important finding, CSB investigators said, because the same conditions of differential pressure could occur at other drilling rigs, even if a crew successfully shuts in a well. The CSB warned this could make existing blowout preventer designs less effective in emergency situations. In the case of the Deepwater Horizon accident, the buckled drill pipe prevented the blind shear ram from sealing the well. Oil and gas from the well flowed out of the buckled drill pipe and into the Gulf of Mexico for 87 days. A reported 5 million barrels of oil eventually spilled, causing one of the worst environmental disasters in United States history.
Now, pay attention to the environmental impact. Two important questions hanging in the mind of every student by now. How oil is bad for the environment. Do I need to worry about that even in those challenging operations? Definitely, yes. If you find difficulty in running a smooth workflow and refined logistics, so you are stuck in nowhere sometimes, as help in emergencies might take a long time or never come due to. Those locations are usually remote and environmentally challenging. The adverse effect of oil on the ecosystem is visible. Oil spillage is lethal to living organisms. Oil pollutes water and air. Combustion of oil derivatives is hazardous to communities as emissions penetrate and react with bio and geo-environmental components. The oil and gas industry affects wildlife habitats and damages landscapes. A closer look at technical challenges. Water depth is not the only obstacle in challenging drilling operations, but the temperature and pressure of the formations to drill is another challenge professionals need to pass through in the game. Hot temperature and elevated pressure in challenging projects can grow in difficulty in ultra HPHT and extreme HPHT conditions. Geomechanical stability referring to seafloor and wellbore is another challenge that can affect the progress of the whole project. Harsh climate and topography are another game changer in project degree of difficulty. Drilling tools and drilling rig capacity and durability during challenging operations can shift the whole project between demise or success. The degree of crew training and safety awareness is a project saver. More challenges will be revealed during the course. We can visualize them in the following list. Location remoteness from nearest base or harbor. Logistics and workflow. Drilling window and equivalent circulating density and narrow drilling window. Circulated drilling fluid volume. Supercharging, ballooning, of formation. Plus, the regular drilling problems like pipe sticking, loss of circulation, mud contamination, formation damage, hole cleaning difficulties, acid gas's detrimental effect on fluids and metal components, H2S bearing zones and fatality concerns, shallow gas zones, well control issues, surge and swab pressures, fluid compressibility, thermal expansion of fluids and components, gas solubility, barite sagging. During the course, we shall go through those listed challenges one by one and comprehensively. Thank you for listening. If you seek a human trainer, please click on the button labeled Live Training.
Remember, the world is an astonishing place, and you are the heart of that place.